Hello, I'm Botond Antal, and I'm giving this talk from Stony Brook University, New York. I'll be talking about brain aging from a metabolic perspective, and I'll also talk about relevant interventions to halt the brain aging process. So, no surprise that brain aging affects all of us sooner or later. It's manifested in sharp cognitive decline. When we look at the underlying changes, we observe structural deterioration along with hypometabolism, which has implications on the mechanism of brain aging. The idea is that aging brain becomes energy constrained, and that's what leads to age-related deficits. Specifically, the hypothesis is that insulin-dependent glucose transport, which neurons do rely on to a large extent, breaks down, and this way it deprives neurons of energy. Logically, one of the solutions would be to bypass broken insulin-dependent pathways with alternative fuel source. Ketones are the primary candidates, as these molecules are readily utilized by neurons for energy. In a recent study, we actually showed that age and diabetes-related effects in the brain significantly overlapped in terms of cognition, structure, and brain function alike. This suggested that brain aging is indeed to a large extent a metabolic deterioration analog to diabetes. So our goal has been to see if we can halt brain aging with ketones, and to test this we needed a biomarker which can act on shorter time scales. This way we can hone down on energetics and parse out processes acting on longer time scales, such as inflammation or structural changes. With these constraints, we utilized a functional metric which I'll be referring to as brain network instability from now on. This metric quantifies how fast brain networks are changing over time. We hypothesized that normal cognition requires a certain extent of stability of brain networks, and the energy-deprived brain will deviate from that. First, we assessed whether this metric would change as a function of age, and we saw robust trends across age in large public neuroimaging datasets. With EEG, we observed a significant increase in older people, and the fact that EEG measures neural signal would imply that there is a neuronal component besides vascular or other potential contributors. With the fMRI datasets, we were able to derive a better resolution across age, and interestingly, we saw a nonlinear increase with a sudden destabilization in the middle age group. Next, we proceeded to test whether we can modulate brain network instability with ketones and reverse the previously established age-related effects. We utilized a within-subject experimental design where we have people coming after an overnight fast and consume exogenous ketones right after and right before brain scans. This way, we can see what ketones do to the stability of brain networks. Besides ketones, we also tested for calorically matched glucose to hone down on ketone-specific pathways. And we ran this experiment both with EEG and fMRI. With both imaging modalities, we observed that ketones reversed the aging-related destabilization of brain networks. Again, the positive results in EEG suggest that ketones modulate brain network stability through neural activity. Furthermore, this effect was specific to ketones, whereas with glucose we did not see any changes. Furthermore, our fMRI dataset allowed us to evaluate treatment effectiveness in different age groups. And interestingly, we observed that the stabilizing effects of ketones were specific to the middle age group, which actually coincides with the critical point we saw earlier in those age trends. This result suggests that metabolic interventions aimed at curbing brain aging are only effective up to a certain age, and beyond a certain breaking point, they become ineffective. Lastly, I want to touch on some exciting results we collected in mice. So as our previous EEG results already hinted at neural effects, we utilized electrophysiology and brain slices to explore what's really going on in neurons mechanistically. We looked at conduction velocity, which is essentially how fast electric signal is propagated between neurons. And we did these measurements in the hippocampus. We observed that if we evoked insulin resistance in these neurons by blocking GLUT4, the insulin-dependent glucose transporter, conduction velocity dropped. However, consistent with our human results, once we added in ketones, we were able to restore conduction velocity to its normal levels. And if we added ketones at higher concentrations, we were actually able to increase conduction velocity beyond the normal levels, essentially supercharging the system. Again, suggesting that ketones can rescue neurons from an energy-deprived state. And with that, I'll close out this presentation. Here is a quick snapshot of our team, and if this talk inspired you or you would like to collaborate with us, feel free to reach out through our website, lcneuro.org. Thank you.